David Lees, and if most of you saw Tamar's keynote this morning, I'm going to switch from, we work on same project, or at least a couple of the same projects, including the ground data systems project that she presented this morning. But I'm going to switch from talking about a future lunar mission to an actual, what NASA calls an analog mission. Like, this is practice for a future mission to Mars, and I'm going to talk about how we did it work underwater. And one of our colleagues, Matt Deans, will always say that no analog is perfect, and despite the fact that this one is in water, it's really intended as a model for exploration on Mars. And the things that are interesting from a NASA perspective for this are both the stuff that we find in the lake, which I'll talk about more in a second, and also the fact that it is a real harsh environment. It's water rather than, you know, a place with no air or weird air like, you know, like the moon, or no weird air like Mars. But people have to have life support if you're sending divers in or be in submersibles. So this is the sort of angle that NASA's interested in. It's also a good sort of earth science project because this lake is really good. You can see it's a pretty mountain lake, but it also is unusual. It grows these things called microbialites, which are like stromatolites or in caves. They're not actually coral, although they look like it, but chemically or physically they're similar to stromatolites. And it's unusual because this is like a perfectly clear, it's what they call oligotrophic. That's not much algae. It's this clear, clean mountain lake, and usually these things are found in much more alkaline water. So the science angle of this is also important. So we had this challenge of trying to build technology that could support real science in a harsh environment, which is, you know, exactly, you know, is a great analog, at least for that aspect of doing a space mission. And what you see with these microbialites is that they vary a lot with the depth of the lake. They range from these sort of like less interesting, like one of the scientists on the project said her husband called them space potatoes, like the upper left ones. And then you get these cool like artichoke formations and chimneys down deeper. So the science challenge for this was that these guys, they started out just recreational divers found these, and they realized they wanted to survey more of the lake. And the year before we got involved, they took 2 submersibles down with HD video cameras and collected about 70 or 75 hours of video. And I'm showing you the good pictures. A lot of the stuff, there are like long stretches of just muddy lake bottom, right? And so this was like one of those awful grad student jobs where someone had to basically go through this video frame by frame, or like they took 5-second chunks out of it and classify it and throw out the ones that were bad and mark, you know, and then they did have some GPS data, but again, it was all manually correlated. So we ended up taking some of the technology that we developed for robots, where you have this autonomous vehicle where you need it fully instrumented and trackable, just to make it work, and try to adapt it to help them with this project so that they could process their data much more easily. And in fact, our big goal, and will be important, like in the mission that Tamar was describing this morning, one of our big goals was to give them enough like preliminary analysis while they were out there, and this was typically like a 2-week deployment out in the field, enough analysis that they could make decisions on the fly, like, wow, we got really good data today, we should go back there, or that was not so useful, you know, we shouldn't. So these questions, or these are kind of the questions we were trying to support by bringing some technology to this project. And we did it using the tool that you heard about this morning, Exploration Ground Data Systems, which was a set of web-based tools. We have this very distributed science team. They sort of go up into Canada. There's one guy from New Zealand. So we really, all of the usual stuff about web tools really applies here. You want people to be able to collaborate remotely, to share what they're seeing. They start out, we also try, like a lot of NASA tools, on the real missions tend to be sort of fairly siloed. Like there are people who are responsible for driving the rovers, they're the science team, and the connection between the two is often a little bit loose. Like the science team will use one tool and say, as geologists, we think this is a cool place in Mars to explore, and they'll basically throw this stuff over to the rover drivers who will use a different set of tools and simulation, say, well, you can't do that, or you're going to hit through this rock, or you're not going to fit through this gap you're trying to get into. So we tried, we were trying to do sort of an end-to-end but high level. Like what we stayed away from was trying to be too, sort of like trying to reinvent MATLAB or some, specialized analysis tool. But we did want to integrate data well enough that people could plan what they were doing, run something and see what was happening, and then quickly go back and find things. And some of the things they found, they might want to export later to use for more detailed analysis and specialized tools. So this was sort of like our quick picture of the workflow that we're trying to support and that we did try to support in the lake. So I'll quickly walk through sort of the phases of this project and then talk about how we actually built some of the maps that you're seeing. So that, like, in the initial, like the purple line, the planning phase, and then monitoring and archiving is collecting, storing the data, and then exploration, and you can see some notes that people took on data after. You want to come back afterwards and see what you saw, pull up the video you care about. So initially, actually, well, the very first thing, like I said, was human divers just went into the lake and said, hey, this is cool, we found some cool stuff. We should tell some science people about this. I mean, that was more or less, almost how it happens. A professor at University of British Columbia heard about this lake from recreational divers. So the next thing was Art Trombanis, who's a professor at University of Delaware, took this autonomous underwater vehicle that did surveys in a decently high res. I think, is it like a meter? Do you remember what? I have no idea. I think it's roughly 1 meter per pixel, like sonar, but you get sort of rough thing. You can get a general sense of where things are in the lake. So this was what people used, that, and then it also built pretty nice bathymetry maps. And this is what people used to figure out roughly where they wanted to go, like areas that looked promising. There was also some manual markup of the sonar data with things that looked like it might be. I think after they had taken the subs down the first year, you could see certain patterns that looked like rock slides or things that might be interesting to go back into. We also provide support for like having humans mark up the maps, like areas that they want to go to or keep out of. So all of this stuff can be done, and then the people, your remote collaborators can then pull up the same markup or data in a web browser and see what you're planning to do. And then we pull all this stuff together and basically build a simple map of where we want the submarine or the ROV, the remotely operated underwater vehicle, to go. And we can also add on to that with tasks that we wanted to do, like take a picture of this or do something like that, imaging tasks. And we mark up these plans, and again, this is a reference for people, and then we go out and run them, and what you can see is that this was an example of a live track from one of the submarines, one of the deep worker submersibles that we used on this project. This is like a human sits in here, and there's tracking. And you can see where they were. You can see people can take notes on the fly, the little envelopes of observations that the subpilot is calling up, and these are all geocoded and located. And you'll see the blue line was the original plan. And because of the sonar data, because you don't see that well underwater, typically the plans were an approximation. It was kind of like we saw something interesting in the sonar. You get down there and you see there's rocks in the way or there's this. So a lot of this was done by the subpilots. So we really needed to know where they were going. And again, this was all mapped in Google Earth, and we've since switched to open layers. So you could pop up bubbles with still frame grabs or video playback of the markup that you saw underneath the lake. We had live video in the last couple of years we were there. We ran ROVs, so you could see, and divers, so you could see cameras over the divers' shoulders. If you look really carefully, the ROV was staying back for safety, but you can see a diver there from the ROV's view of the world. And as people were taking notes too, this was something that Tamar actually cooked up while we were at the lake last year. You could broadcast notes from, like if I took a note and someone else was watching the same video feed, they could see the note pop up while we were working. So we used SSE to do that, and that was a new addition. That was like a request we had for several years. So we're working on beefing that up. And you could also afterwards, if you rather than a map view, in addition to the map views, we had sort of these temporal views. You could search on keywords and see notes and thumbnails that were grabbed to the video, or just click to play back your video. So that was sort of like the end result. This was the tools we built in this, and now I'll quickly go through how we did this and what we used. So we used, this is the AUV that did the initial surveys of the lake. These are the NUTCO, the submersibles, the Deep Worker 2000s that came along later with pilots, and they were followed around by this chase boat. If you look back, right in by the light back here, there's a sonar transducer to track the vehicle, and you can see the top side, this orange thing, and the antenna on top for GPS. So we use this boat to track our underwater assets. And then the last 2 years, we went out again with ROVs and divers. And again, there's the sonar transponder on the top of this. The divers we tried to track, and that was a big challenge. And they always had to stay close to the ROV, so we ended up using that as our position reference. You can see, will this work? So this was like, I'll quickly show a little bit of this clip, if it plays, of diver sampling. Is it? It wants to, PowerPoint, isn't it? If you want, so you can see, I'll just describe it. Someone is grabbing a microbialite sample and putting it in a box, and this camera's on this person's shoulders. The other diver's got a handheld camera with another view, and at the same time you can see the track of where the ROV is, and again, the ROV's view of the diver. And then quickly, how all of this stuff worked, as you saw from the pictures, right? The USBL tracking there is there's a satellite antenna. The boat gets a GPS location, and then you have a sonar transducer hanging in the water from the boat and a transponder on the vehicle. And with this, so you get a vector from the boat down into the water. When it's properly calibrated, you get about 3 meter accuracy, 2 to 3 meter accuracy, which was just enough with the murkiness of this water that we could find stuff again and go back to it. Basically, the big issue with this was if you look at the angle at the top, right, you've got basically this long arm reaching out into the water, and so a slight bit of miscalibration, and like if you think this is forward for the GPS and the sonar thinks 5 degrees to the right of that is straight ahead, you get pretty substantial errors when you get out 50 or 60 meters. So part of the reason for the boat, you reduce that if you're sitting right on top of the submerged object, and also we did like our very best to calibrate those errors out. This was like a pre-calibration run, and you can see that we dropped a beacon on the bottom of the lake and drove the boat in figure-8 circles on top, and the beacon, even though it was fixed as the upper left page, still looked like it was spinning around in the water. So, and then we just used NumPy and Python actually to SciPy to optimize that's sort of like an angular offset curve showing the minimum point. And after we did that, we actually squoze down the error a lot. We got about a 3 standard deviation error of about 1.2 meters last year after we ran some calibrations. And that, ended up working out, again, it gave people enough information to be able to like send someone down, divers down in the morning, let's say, identify a sampling site, and come back in the afternoon and actually grab a sample. And we were really pleased that we were finding stuff again. With this, so that was great. A quick comment about Google Earth and open layers, that we made this migration. Again, I think if some of the cesium folks were pointing out, they got a big jump in interest after Google Earth decommissioned their plugin, so that's what drove us to do this. We came into work one morning and our planner didn't work anymore, so that was like a good push. But we've been happy with open layers. Open layers took a little more work to set up, but I mean the Google Earth API, the plugin, in some ways was limited for doing things like drawing all this markup. So we've been, I think, very happy with open layers as an alternative. We found in the end that we could get back to the science points of interest we wanted with this. It's not cheap, but there are much fancier underwater tracking systems in this one, and this one did the job. We got the notes and video correlated. It really improved the science productivity a lot. And as a first cut, we found actually the 2D maps were okay, which was a little bit of a surprise. Where'd it go? A little bit of a surprise to us, because the lake is very 3D, but you really care about stuff on the bottom. So that helped a lot. That said, we're very excited about trying to see if there are ways we can integrate tools like cesium into our work, because there's stuff that you just can't. If you're looking at water columns or shadows, if you just want to get a feel for the steepness, there are areas where the 3D really helps. So that's definitely an area where we want to head in the future. And wait, I did it, more or less, maybe a few minutes though. So anyway, you want to add some stuff?
Yeah, I do.
Does that work?
Is this working?
Now it is.
So do you want to talk a little bit about the size and depth of the lake? Because I don't know if you guys have ever thrown a quarter into a swimming pool and been like, right, I'm going to go find that. It's hard, right? This lake was what? It's
6 kilometers long and about 1.5 wide. Yeah, so that's a good point. It is, the deepest point is about 180 feet.
Okay.
It's pretty.
And this is one lake that we've explored. There's also another sister lake nearby that we also explored. And it's murky. It's not clear like a swimming pool. So basically, you'd send out your submersible or your ROV and go and find these really cool structures, and then the scientists would decide, yep, you want to take a sample from that particular one. And it was our tools that let them go back. We know it's roughly in this area, give or take 3 meters. And we know what depth it's at. We have really accurate depth readings from the diver tools and so on. So they could go to that rough area, go down to depth. And some of them had this amazing like mental map and recollection, especially our ROV pilots.
The pilots were good.
Incredible. Because they're just sitting on this windy chase boat, spinning in circles in the waves, like under this hood, looking at these screens. We don't have pictures of that, but driving.
Yeah, there's one picture actually.
Seen landmarks.
They are.
Say like, right, I recognize the shape of that one microbialite among thousands, and that's the one the scientists want.
Yeah, in
Lock
fact.
the ROV down, and then the divers will take a sample.
Yeah, exactly. In fact, I was going to say that one of the reasons that we learned that the calibration was really important was we first showed up and with sort of this, well, in our defense, I'll say that Tamara and I were both a little concerned about that. The guys that were managing the hardware were like, oh, sure, we'll get this tracking working, no problem. And we went out there, the ROV looked like it was hopping all over the lake. And a couple of times, like the divers, or one of the guys who was a really experienced diver just looked at the camera and said, it's a little to your left, go over that one. Yeah. So we really, we were happy to work the kinks out. Yeah, it is. We might even be able to find a quarter if we're really, we found fishing poles and sunglasses, golf balls.
And like a lot of beer cans and really old tins. Another thing is that our team at NASA does amazing things. They provided a Wi-Fi network over the entire lake. So yeah, so that's how we got the data back, and we would introduce like a 2-minute delay. So we're on this boat spinning around, and like there's one point I was like, I really like being on a boat. I want to buy a canoe, and so I went on Craigslist and I emailed my husband and was like, we bought a canoe because of the Wi-Fi network on the lake. So that was pretty awesome.
Lots of useful functions that it has. So should we take? Did you have a question? Yeah.
A question about the sonar and the lake technique that you explained. Wouldn't you think more accurate to have 3 GPS and 3 sonars and 5 delay?
Yes, definitely. So this technique is called ultra short baseline sonar, and it's done because it's relatively straightforward and easy and cheap. Yeah, the other thing, long baseline sonar does exactly that. There are several beacons spread around the lake, and it does the same kind of triangulation, and it is much more accurate. It's just more expensive and difficult to set up.
The other problem that we have with sonar is that it reflects and bounces back, especially off the shore of the lake, or if you get too close to a lot of these microbialite structures.
Yeah. In fact, the guys that we worked with the submersibles, their sort of day job is doing a lot of underwater construction. I mean, this company is actually in Vancouver, BC. They had a contract to do the New York City water supply. That was theirs. They have a pressurized dive suit as well, and they put divers down at night when people weren't running water and flushing as many toilets. So they were kind of annoyed at this lake. Like, this is a stupid, shallow, tiny little lake. Like, we work on ships, right? Because the sonar, because the lake was shallow and it's like this narrow, steep, there was all kinds of reflection. Like, they were used to working in thousands of feet of ocean water mostly. I think in the pipes they didn't have to track. But, they did a lot of underwater construction and, undersea cable inspection work. So everybody kind of had to improvise for this work. It was interesting. Anything else? Okay.
Thank you.
Thanks a lot.